In the early 80s, video games were already a favorite pastime for kids.
Very played every day.
How much a week?
40.
At the same time, personal computers were suddenly a viable purchase for the home. These computers came with BASIC built in, a programming language that brand new coders would find easy enough to learn on, and which could manipulate color graphics right on their TV screens. Video game addicts could now make their own video games. Today, we compare the basic languages that came with the Apple II and the TRS-80 Color Computer, and the differences in how they chose to support color graphics. In the process, we will see just how weird the experience of writing graphics programs in BASIC was, limitations of the hardware, and interesting choices in how BASIC abstracted the hardware from the user led to some surprising and downright strange results. We will also delve below the BASIC layer to understand why things got so odd. The TRS-80 Color Computer, or CoCo, was my first computer, and it's where I learned how to code. But I also loved the Apple II. Not only was it a pioneer in so many ways, but I just loved its games. When I got access to one from school, it just seemed more mature and advanced than what I had at home. The Apple II line premiered in June 1977 with the 4K model for about $1,300. It came with integer BASIC, because that was faster than the floating point BASICs, which supported numbers with a decimal point. Games would never need decimal numbers anyway. By June 1979, a floating point BASIC called AppleSoft came standard in the Apple II Plus. Now 48K of memory for about $1,200. This model also added more colors, so this is what we'll be using for our comparison on the Apple II side. The 4K CoCo 1 premiered in the fall of 1980 for a mere $400. But we're going to skip ahead a few months to early '81, when you could get a 16K CoCo with extended color BASIC for $600. This upgrade was the first time you could control high-resolution graphics on the CoCo from BASIC. By comparing the Apple II Plus with AppleSoft BASIC and the CoCo with extended color BASIC, we have more of an apples-apples comparison. Or apples CoCo comparison. Now I know what you're thinking. This channel is called CoCo Town. There's no way that guy is going to be fair. But I will have you know, every morning I wake up and I look in that mirror on the wall, and it tells me I am the fairest of them all. Maybe the CoCo with extended color BASIC had an unfair advantage, since it did come out a year and a half after the Apple II Plus. But maybe the Apple II Plus has an unfair advantage because it was still selling at the time, and for almost twice as much. I can't really make you okay with this. You're just gonna have to do some soul searching. Both the CoCo and the Apple II have a low-resolution mode and a high-resolution mode. The high-resolution mode allows for greater detail, but uses more memory and offers fewer colors. Let's start with the low-resolution mode. The CoCo's low-resolution mode gives us 64 by 32, that's 64 pixels going across by 32 pixels going down. The screen requires 512 bytes of memory. We get to choose from 9 colors, including black. The Apple II gives us a resolution of 40 by 48 and uses 1024 bytes of memory, double what the CoCo uses. But look at what we get for our money. 16 brilliant colors, including black. Even after you allow for the fact that it cheats by listing gray twice, this is still a significant improvement over the Color Computer. Let's check out how the basic code behind these kaleidoscope programs compare. The CLS0 command clears the screen to black, and we can change the 0 to any number up to 8 to choose the background color to clear to. Many games would simply cycle through the different CLS colors as an explosion-like effect. We've got less choice on the Apple. This simple gr command brings us into low resolution graphics mode and clears the screen to black. Setting pixels is similar. On the CoCo we use set with the coordinates and a color, or reset if we want the color to be black. On the Apple, we use plot with the coordinates, and set the color beforehand with a color equal command. This works for black too. But things start to get weird fast. If we let the kaleidoscope run on the CoCo for a while, we start to notice something strange. Let's compress time by kicking the emulator into turbo mode.
Here we go.
Do you notice how the image has gotten more blocky? Each of these blocks is the size of 4 pixels. Why do we end up with these solid color blocks in so many places? On the CoCo low resolution screen, we're not actually manipulating pixels. We're printing what they call semi-graphic characters. Each character is the size of a letter, but contains 4 low-res dots. And those 4 dots must be the same color or black. We can't mix red and blue, for example. In fact, the worksheet in the back of the manual visually groups the pixels into these character blocks, so you can design your pixels with this color limitation in mind. So what exactly was going on here? Why did things start with the smaller pixels and then gradually become these large clumpy character blocks? Imagine we want to set just one green pixel on the screen. But now let's put a yellow pixel right next to it. There's no option here for a character that has a green on the top left and a yellow on the top right. So since we're going to set yellow now, yellow wins, and the closest fit is going to be this character. So now we get this. And let's say we want to put a blue just below that yellow. Again, we can't be mixing yellow and blue, so we're just going to have to pick the one that's all blue. And if we want to put a red in that last spot, it's all going to turn red. As more and more dots are set on the screen, characters get filled in, forcing their contained dots to be the same color. But the Apple II does not have this problem. If we run similar code, we get the results we'd expect. Let's start with a magenta pixel. Then to the right of that, let's do dark blue. Just under that, purple. And then to the left of that, dark green. No problemo! In fact, it goes further than that. The low-resolution graphics screen on the CoCo is the text screen. The text characters and the semi-graphic characters coexist. We could even have our kaleidoscope program print out messages interspersed with the colored pixels. But the Apple II has quirks as well. By default, you don't actually get a full 48 rows of pixels, because the bottom 8 rows are taken up by an independently scrolling text region. It's like you get a command prompt that controls a graphics window, all on one screen. This is a great way to interactively experiment with graphics commands, and programs can print and even receive input from this bottom region while displaying pictures on the top. You can force the entire screen to be dedicated to the low-resolution graphics mode, but to do so you have to go around BASIC to do a weird poke and machine language subroutine call. Overall, Apple II wins this round. It gives you way more colors and way fewer limitations when it comes to resolution. And I find that scrolling text region at the bottom a nice benefit, even though they lose points for not having a dedicated BASIC command for disabling it. What else can we do in low res other than just plotting points? Both the CoCo and the Apple have ways to query what the color of a particular pixel is. This can be useful for hit detection in games. But the Apple takes it one step further and offers commands for drawing horizontal and vertical lines. You can't draw lines at any angle, but even just being able to do perfectly horizontal and vertical lines is nice. And the only way to do this on the CoCo is to draw the dots yourself. Basic loops be slow. Again, Apple II wins this round. We saw the low resolution mode had some weird quirks on the CoCo. But as we move into high resolution, we are kicking the quirks up a notch. From here on out, everything is some level of weird, so mentally prepare yourself. You may want to start your daily affirmations now. When we put the CoCo into high resolution mode, we get 128 by 192 pixels, and we get two choices of 4 color palettes. The primary color palette you see here, and the pastels palette you see here. Incredibly, neither of these palettes give you black. You do have the choice to go up to the 256 by 192 highest resolution mode, but this is officially only black and white. However, because of NTSC composite color artifacting, you can get reddish orange and blue by placing your pixels just right. But once you decide to use color artifacts, you're effectively lowering your resolution back down to 128 by 192, just like the other video mode. Check out this video on artifact colors for more information. These high-resolution screen modes require a whopping 6K of memory, compared with only 512 bytes for low-res. You enter high-resolution mode by using these two commands. They combine multiple functions in a way that's unintuitive at first. This number chooses the video mode for all the drawing you're about to do. We're focusing on 3 and 4 since they're the closest to the Apple II. But you can pick smaller numbers to get fewer pixels and free up some memory. Your color palette is this number in the other command. You can choose between the primary colors and the pastels. This number has to be 1, or else you'll switch back to text mode. And if you issue the P mode command without a screen command, your drawing will all occur off-screen. I won't even talk about this number until later because that's enough for now. Finally, if you want to clear the screen, you use this command with the number that tells what background color to clear to. The Apple II is much simpler and in some ways more powerful. You get slightly higher resolution at 280 by 192, and check out all these colors you can have on the screen at once. So how do you enter high resolution graphics mode? That's it. Just this one command, no choice of resolutions, no palette change command, and there's no need for it. You have 6 colors. This uses 8K of memory, which is a lot of memory back in the day, and which is 2K more than the CoCo uses. But oh, how nice to have all those colors! Setting pixels is similar between the two machines. On the CoCo, you use the pset command to pick the coordinates and color, and on the Apple, you use the hcolor command to set the color, and then the hplot command to draw the pixel. You'll notice that the high-resolution graphics command on the Apple start with H, which I assume stands for high resolution. The graphics commands on the CoCo all start with P. I don't know what P stands for, but I like to think it stands for Philip. And this is where things start to get really weird. Did you notice that the Kaleidoscope app on the Apple high-resolution screen isn't fully symmetric? The left half is not a reflection of the right half. What's going on? Is there a bug in my code? We're going to look at some clues, but pause now if you want to give it some thought before our first hint. If we change this width from 280 to 279 and rerun, now it's fine. But the width really is 280. And if we look in the code, we reflect from left to right by taking the width minus 1 minus x to get the new x. So, with the width back at 280, the minimum x-coordinate of 0 properly reflects to the maximum x-coordinate 279, and vice versa. So changing this to 279, even though it seemed to fix the symmetry, is wrong, and keeps the rightmost column black. So why did it work? Here's your second hint. If width is 279, then width minus 1 minus x and x will both have the same parity, meaning they're either both even or both odd. But when width is 280, width minus 1 minus x and x have opposite parity. For your next hint, here are a couple of lines. Except actually, this is 3 lines. 3 green lines! We set the color to green, and then this command will draw a solid line from left to right on the top. But then the middle line is a dotted line where we're only doing the even x-coordinate pixels. But it is still green, it's not black. And on the bottom we do another dotted line, but this time only the odd x-coordinate pixels. What happens if we paint all 3 lines purple? All 3 lines white? All 3 lines orange? All 3 lines blue? And all 3 lines the other white? Now let's run through those colors again, but we're going to start the screen off with solid white lines before we start drawing our colored lines. Notice how this time we get green in the middle, whereas before we got green on the bottom. All the colors are going to be reversed. The AppleSoft Basic Manual tries to warn us with this comment here. A high-resolution dot plotted in white will be blue if the x-coordinate of the dot is even, green if the x-coordinate is odd, and white only if both xy and x plus 1y are plotted. But this is only scratching the surface. As the parity changes when we reflect from left to right, the pixel goes from a color like green or blue to black sometimes, breaking the symmetry. On the CoCo, regardless of what I set the width to, the worst that can happen is the reddish orange and blue might swap from left to right. But the symmetry is still visible. I'm not going to get black. But it gets weirder. Although we can have all these colors on screen at once, there are even more limitations. We've established that if you want green on a black background, then you just need to h-plot the odd x-coordinates green, and you'll get a solid green line. Same deal with orange. Odd x-coordinate pixels should be orange, and the rest should be black. And in this app, we do exactly that. X takes on the odd x-coordinates from left to right, and we plot those in green at y-coordinate 10, and we plot them in orange at y-coordinate 60. But then we take it a step further. At y-coordinate 110, we alternate green and orange. We have our x-coordinates go up by 4. At x, we'll plot green. We'll leave x plus 1 black. At x plus 2, we'll plot orange, and then we'll leave x plus 3 black. We should expect to see green and orange alternating on that line at the bottom. We can see our solid green and orange lines quickly forming, but take a look at this alternating line. Those are much wider than single pixels or even double pixels. And in fact, as it draws, it's changing itself. Look closely and you'll see a green become an orange. And if we run the same experiment with blue and purple, we get the same bizarre effect. Something more than just even odd x-coordinates is going on. It's like there's 2 4-color palettes, and each line is separated into chunks where you can't mix the palettes. And it gets weirder. In this simple app, we draw 4 horizontal lines. The first at the very top of the screen, the second just below it, the third just below that, and then just below that. And they're each in a different color. Since the lines are solid horizontal lines, we shouldn't run into any of the issues that we've seen before. So try to take a guess at what you're going to see. Well, this is what we get, but if you take a look at the right side, it looks rather jagged. And if you take a look at the left side, it's this perfect diagonal. We start toward the left at the top, and then we diagonally go down to the right. And once again, if you look at the code, you'll see each line always starts at x-coordinate 0. Why the diagonal? We're about to peer underneath BASIC, so things are about to get more technical. If this isn't your cup of tea, feel free to skip ahead to the next chapter. You won't need to understand any of this in order to enjoy the rest of the video. All of this weirdness can be explained once we understand what's going on underneath BASIC. The Apple II sends out a signal to the monitor or TV based on what's stored in screen memory. Like all memory, screen memory is composed of bytes, and each byte is composed of 8 bits. Up at the top, I'm showing the first 2 bytes of screen memory, but I'm showing the bits in an order kind of reverse from what we would normally see. We're starting with the least significant bit on the left and moving up to the most significant bit on the right. And of course, the bits are numbered from 0 to 7. Since these 2 bytes represent the very beginning of screen memory, they're stored at address hex 2000 and hex 2001. So let's say we wanted to store green. The bit pattern for green is 0, 1. So by storing a 0, 1 here, we get our first bit of green at the upper left of the screen. And if we wanted to extend that with some more green, we would store another 0, 1. More green, another 0, 1. The most significant bits that are highlighted in white are reserved for another use, so we can't use those for color bit patterns. So for the next chunk of green, the bit pattern is going to straddle the 2 bytes. So we'll have 0 in the first byte and then 1 starting off the second byte. And continuing forward, we can add some more green, and finally we got a whole bunch of green. And you'll notice that the bit pattern for black is simply 0, 0. We can of course mix a bunch of colors together by using different bit patterns at different positions within the byte. So for example, these bits will start us off with a bit of green, then a bit of black, a bit of purple, and then another bit of purple. Here's some white, 1, 1, and then a couple more bits of green. So what if those reserved bits were 1? This decides which color set the byte is going to represent. So when that high bit is 1, we get to use the other 4 colors. As before, 0, 0 is still black. But now 0, 1 represents orange. So we've got a couple bits of orange. 1, 0 is going to give us blue. Another 1, 0 gives us blue. Here's some black. And then we ended off with a couple bits of white. So with that established, we can now start putting together the pieces of the puzzle. The first 2 things are crucial to understand. Whenever we issue the hplot command to set a specific pixel, it only sets 1 bit. Each pixel is only 1 bit, but each color requires 2 bits for its pattern. So if I wanted to put green in an even position, let's say at the very beginning of the screen, and I did an hplot where the current color was green, all that's going to happen is this bit will be set to 0. I need to move to the next bit, to the next pixel, and set that to green with another hplot, and now I have my full pattern, my full 0, 1. This is what the AppleSoft basic manual was trying to warn us. It was actually telling us we could set the current color to white, and then by turning on white pixels either at even or odd positions, that would give us the colors. If we set the color to green instead, we still have to do the same thing. The only difference is if we use green and turn on even pixels, they're just going to stay 0 because the bit pattern for green is 0, 1. But there's another factor to consider. Each byte is restricted to only one of those 2 palettes, and that's determined by this reserved bit at the top. If it's 0, we get to use these colors. If it's 1, we get to use those colors. We cannot mix colors from this category and this category in the same byte. And that's why we were getting these weird results when we were trying to intermingle these 2 colors here. So almost everything is starting to get explained away now. But what's up with this diagonal? It's even more pronounced if I set the AppleWin emulator to composite idealized mode. To understand this, we need to go to the next level lower and talk about how the Apple generates colors in the first place. Again, I'd recommend that if you haven't seen this video on NTSC composite artifacting, that you give it a look if you're curious. But I'll give you the very quick summary here. Apple II generates its video picture not by using a combination of brightness information and color information, called luma and chroma, but solely with brightness information, just using luma. By sending black and white pixels of just the right size at just the right distance, the luma signal imitates a chroma signal with the brightness going up and down at exactly the same frequency as chroma. When the TV sees this, it interprets it as color information, even though it really is just brightness information going up and down. These bit patterns I've been talking about aren't just bit patterns that you use to look up into a color table to figure out what color to show. They are literally black and white pixels. Each bit is either black or white. And so it's up to the programmer to arrange them in just the right way that you end up with the color that you want. The NTSC Color TV standard dictates that color is determined by the phase. Changing the phase of the chroma signal, or in this case the luma signal, We'll cycle through the different hues of colors that the TV can generate. A 0-1 pattern is going to be 180 degrees offset from the 1-0 pattern. And this is how the Apple can generate either green or purple. But in order to get the two other colors, the blue and the red, the Apple does this ingenious trick. It uses this high bit to introduce an additional half-pixel delay in the signal that it sends to the TV. This means that the brightness will go up and down just a touch earlier or just a touch later. This half-pixel delay introduces an additional 90-degree shift in phase. And so now we can do blue and red. But because this is all done by changing the timing of when the brightness goes up and down, you end up with these imperfections as to when and where a pixel is going to be drawn on the screen. And this explanation also gives us insight into something else. What if I change that high bit in adjacent bytes? What if I just use this same bit pattern for the color, with the only difference being the high bit changing from 0 to 1 in the next byte? It should give us alternating green and orange, but you can see that there's a bit of this striping going on between them. It almost looks yellow. Similarly, between blue and purple, which are also the same bit pattern, when I change the bit from 0 to 1, we also get these interesting stripes of a different color between them. I'm assuming this is because the timing change can't happen instantaneously, and it's actually happening in the middle of a bit pattern that's being sent to the screen. At least this is what I see with the AppleWin emulator. I don't actually have an Apple II that I can experiment with. For the Apple low-resolution graphics screen, we don't have any of these weird problems, but it is still using NTSC composite color artifacting for all the colors. The reason things go more smoothly here is because the pixels are so big. They're big enough that the Apple can squeeze a bunch of high-resolution pixels inside them. It has more time and more space to do several up-down cycles of the brightness signal to establish the color that it wants. The basic programmer doesn't have to do multiple low-resolution pixels to get the pattern to form. One is enough because the pattern is happening inside. And one final note. On the CoCo, on the P-Mode 3 screens, NTSC composite artifacting is not used at all. The two color sets you can choose from are generated using a traditional pair of signals, a separate luma and a separate chroma. And since there are only 128 pixels going across, they're already wide enough to establish the color with chroma without nearly as much of the weird artifacts and bleeding that you would see with higher resolution pixels. On the P-Mode 4 highest resolution graphics screen, all of the colors are coming from composite artifacting. But the CoCo doesn't have any of these weird, unpredictable caveats because the CoCo makes no promises. There's no basic command to change the color to orange-red or to change it to blue when you're in the P-Mode 4 screen. The only colors you have to work with are black and white. So if you can figure out the patterns and get yourself other colors, good for you. But the CoCo makes no claim to make the colors for you. This one is really close. You can definitely do more with the Apple II straight from BASIC. You can get more colors on the screen at once and it just looks better. But the process of actually doing this from BASIC just has too many unpleasant surprises. The way AppleSoft BASIC chose to expose these artifact colors is just too confusing, and you have to understand what's going on underneath BASIC to have any hope of getting what you want on screen. It was close, but I have to hand it to the CoCo for providing a reasonable and understandable experience for the BASIC programmer. On the CoCo high-resolution graphics screen, you can draw arbitrary lines at arbitrary angles. Use the color command to choose your color, and then the line command where you specify the coordinates of the two endpoints. The CoCo draws a line between the coordinates using the color you choose. It's just that simple. On the Apple, the names might have changed, but otherwise it's exactly the same. Use the hcolor command to set your color, and then use the hplot command to connect any 2 points. And both computers have variants that let you continue from the last line to make it easy to draw polygons and other shapes. When it comes to high-resolution lines, the CoCo and Apple are tied. The CoCo high-resolution mode comes with additional commands for drawing circles, rectangles, flood-filling arbitrary shapes, By the way, see these videos for more information on how that flood filling works. And a command to query the color of any pixel, again useful for hit detection. The Apple has none of this. Well, I guess you can draw shapes by plotting them pixel by pixel, maybe using a little trig, but it pales in comparison to the speed of a dedicated command. The CoCo wins this round in a total shutout. With a point awarded for each win and each tie, the CoCo and the Apple II are both at 3 points. In the next video, we conclude the showdown. We'll compare the machines on some advanced techniques, flipbook animation, self-contained shapes, and motion across the screen. Who will reign champion? We will, because we'll have learned something. Thanks for watching. Or maybe the Apple II Plus has an advantage, because it was still selling at the time, and it was for more than, Maybe the CoCo with Extended Color Basic has an unfair advantage, because it was, If this isn't your cup of tea, I'm going to have to wait until that garbage truck is done, aren't I? Now let's cycle through all the colors, and we're going to do 3 lines at a time. 2 Plus with AppleSoft Basic, and the TRS-80 Color Computer,